we are going to see can crash. So let's start to import the geometries. Let's the crasher. So after creating individual parts, go to discrete rigid. So then to here, we need to create a reference point. For that, we need to create a midway point. So it will be easy for creating a reference point. So let's create a reference point for this, and then let's insert the part of base plate. So it's also created as individual parts and then attributes as discrete rigid. And then for this too, we are going to create a reference point using datum points, which is in between two. So let's take the reference point, and then now let's import the main character scan. So let's click it and then part out of deformable. So just go in and then that's it. So now as per the property, we are going to take a discrete the thing like a steel Johnson group. So we are going to use this material for this. Then as we see it, the density which is in ton per mm, and then elasticity which is in MPa megapascal, and then this is Johnson Cook's material data. So as you see, we are going to proceed with this material data, and then let's create a shell thickness of 0.5 for the can, and then let's assign it the shell thickness of it. So now to create uh, inertia for this. So basically we need a inertia for the functionality of this. So let's get as a reference of 0.5 for the inertia, and then let's go for it. And then now let's go for assembly. So let's assemble all the all in independent, so that will be easy once you entered in. So let's check the position. So these geometries are plainly aligned. Let's go to non-perspective, so it will be easy to have a good look. So let's create a step. Basically this is actually dynamic analysis explicit. So let's get into it, give a timeline of 0.01, and then jump on create yes. So in history output, sorry, field output, you can actually select whatever the thing that you want as an output request, and with the interval of a 20, so which creates a decent number of plots that you can have a good look at. So if you want more number of plots in between that, you can actually come up with a pretty lesser numbers. So now interaction. So generally we need to create a property for the interaction. So let's take tangential, which is penalty with a coefficient of 0.25. So and then mechanical hard contact behavior, so which will illustrate. And then let's go to create a gentle contact instead of surface to surface gentle contact, pretty much good and explicit. So assign the friction and then go. And then now we are going to give a tie contact between these flows, because we don't want that to be moving here and there. So let's create a master surface of this one, create brown, and then slave surface selected, which is also brown. And then let's create one more tie for the upper one. So let's select surface and then select all these three regions, and then done, which is in purple in color. So give purple and then select the slave surface, which is this, done, which is in brown in color, and then assign it. So now interaction area is over. Let's go to the loop. So let's create initial mechanical symmetric thing. So let's take this boundary and then give set and cast it. Okay, and then let's create one more in initial. Instead of symmetry, we go for displacement and rotation. Continue, and then we are going to see this. The reason behind we take it in initial, we can either modify it in later on stage, because like at initial it's supposed to be on the idle position. So this one is the other one. So let's take, we are going to give 19 71, and then with some amplitude curve that we want to take. So let's take 0 at 0, and the maximum times step that we have given is 0.01 at 1. So this will function it. Right, we have actually modified it. So let's go for mesh. Now we are going to create a mesh for this. Let's take we are going to give amount of like 5 as a global, and then for this we are actually going for around 8, and then for the can, so we can consider for the can as 3. So the more you go lesser number, it actually creates the more accurate results, but at the end of the day it actually also drag your analysis more to finish it off. Let's assign the element type that which is explicit that we are going to do. So, which is explicit, and then let's take can replace, and then let's take this for explicit redux integration, and then with a shell element, right? Okay, so the definition of the elements and then types are done. So next will be running job. So let's go here, create, we can give a name as can crush, and then you can go for the parallelization, use multiple cores for better running, then you can go direct summit, and then you now see the monitor for the further updation. So it will show you the status of the running along with the functionality which is going to behind happen. Initially, it actually starts with deck recheck whether the input users are good or good to go for the run. So now it has the access to run, and then it starts to display the number of timings, step timings, and then increments, total time taken for it, and then the kinetic energy statements. So each and everything will be illustrated over here. Now you can see that analysis has been complete. Let's go for results, and then let's see how it actually behaves. Okay, so this is a contour that you can see that can has been crashed perfectly. So let's actually go for a few things. So first and foremost, go to visual annotation option, and then legends, make it convert into fixed. So it helps you out have a regular good numbers that you won't have like confusing state on the fractions. So and let's make it a little bit bigger. Now let's get into over here, and then as and then uniform as value as 1. So that actually gives you exactly the contour actually how it happens, not elemented oriented or like it might be look like a pixelated. So let's run it, and then you can see the element is crushing. So let's reduce the speed of it. Okay, and then you can see the frame by frame how it has been crushing, and then let's take the can alone. So part instance can replace that we have only we can. So how much it has been crashing, and then you can see those things, how it behaves. So as you can see, let's take, you can see maximum principle. So you can see even S12. So you can see the behaviors and things. And then you can see the displacement, how it actually behaves, and then how it actually reacts for it. And then you can actually take a contour for, if you want to take a stress contour, just take it and edit selection. Let's take a node of it. So let's actually pause it and then take a node of it. So take done plot, you actually has the curve. So if you want to have instead of a stress, so you have want to see some reaction forces. So you can see some reaction forces which is on x-axis. If you plot it, or you can actually see a displacement plot that you want. So you can see how much it actually has spent for time being independent. Okay. So as you see that we have actually come up with the behavior studies of the can crush. So thank you.